All right, let's get started. I don't really have too much in the way of announcements, just that you have your homework 3 due on Wednesday. Other than that, I think we're good, although I have a typo there because it says Friday, February 13th. It's due Wednesday. Since this is our last lecture before you submit homework number 3, I don't know if anybody had any questions in regards to the homework. Like I said, this homework is pretty short. Don't get used to it because I know homework 4 is going to be a little bit beefier. But does anybody have any questions on it? You good? All right. I'm not totally surprised at that because homework number 3 is pretty simple. It's just sort of grunt work on some of the ACI requirements. Like I said, it's good to go through this exercise before you do homework 4, which is your full-blown beam design assignment. Okay, so today, what we're going to do today is we're going to utilize the design procedures that we discussed on Friday to do a full-blown design example, start to finish. So I know it's a long time coming. It's lecture 12, and we're finally doing some design, some concrete design. But I think you'll see how what we're doing in this example will tie together not only what we've been doing up until now in this class, but you'll even see how some of the stuff that we did last semester in structural analysis pieces in. So with that, I'm just going to jump right into it. So you all know from last time that we had sort of derived a step-by-step procedure for how to design a beam. We started off last time with the harder process, the more difficult process, which is designing for an unknown cross-section when you don't have a clue what the beam looks like. So you have to determine not only the beam's dimensions, but its reinforcement patterns. So this example is going to be a little bit longer than situations where you know what the beam looks like. You know, if you're using a precast element or you have ready-made formwork and all you need to do is figure out the reinforcement patterns. So this one's going to be a little bit difficult. And so this is just a recap of what we talked about on Friday. We're going to start off computing the factored moments, the demand, the load on the beam. And so in order to do that, we're going to have to make an assumption. We're going to have to assume the self-weight of the beam. Now, the way that we're going to do that is we're going to use some ACI limits to compute some minimum dimensions for the beam. Now, just to be clear, when it's all said and done, honestly, our assumption is probably going to be a little low. In other words, we're going to assume a self-weight, but in actuality, the beam's probably going to be a little bit heavier, which means at the end, when we go back and analyze the beam, we're going to have to sort of iterate on that factored moments. That's just something to be aware of near the end. So once we get the factored moments on the beam, we'll determine the required nominal moment capacity. Remember, we're also going to have to make another assumption for that. We're going to have to assume our resistance factor is 0.9. Now, again, remember, that's desirable. We want our resistance factor to be 0.9, but we don't know if that's going to be the case because it's going to be dependent upon the strain in the steel. Okay? So once we get our required moment capacity, we compute a rho value. That's our reinforcement ratio. We compute that so we can determine how much steel we'll need at the end. We're just going to, for the purposes of this example, we're going to go with the simple assumption of 0.18 FC prime over Fy. Remember, you can pretty much use anything. You can also get a little bit more scientific with it. You can determine a reinforcement ratio to achieve a target strain value, but we're going to keep it simple for this example. Next, we'll compute a BD squared. That'll give you sort of a measure of how big the beam needs to be. It's sort of like an effective section modulus, if you want to think of it that way. And then we'll use an assumed B over D ratio to figure out how big the beam needs to be. So we'll get a width of the beam, a B, an effective depth D, and then we'll figure out H. We'll just assume that that's D plus 3 inches. And so that'll give us how big the beam needs to be. And then the next step is to figure out how much reinforcement needs to go into the beam. So remember, rho values are just the area of steel divided by the effective area of the concrete. So if you know how big the beam is, you can just take rho BD to figure out how much steel you need. And that's where these design aids came into play. So the design aid that you have in front of you, keep in mind it's all on Blackboard, but I figured I'd give everybody a hard copy today because we're going to use it to select a pattern of reinforcement for our resulting design. And so once we get our pattern of reinforcement, now we have the beam. We know how big it is, we know how deep, or know how wide it is, know how deep it is. We know the pattern of reinforcement, but we made a lot of assumptions to get there, so we're going to have to go back and analyze that section, iterate to determine the actual factored moment on the beam and compute its factored resistance and make sure that they're comparable. For those of you in steel design, do you remember when we did tension members and we computed an efficiency of the tension member? We're going to do the same thing here, and we're going to sort of use the same rule of thumb that as long as our efficiency is 90% or greater, we're going to assume that the beam is fine. For those of you who are not in steel design, don't worry, we will get there. It's not too terribly difficult. And then I'm going to skip this discussion on design requirements because basically these design requirements are all lumped into the second table on that design aid, which determines how wide the beam needs to be in order to accommodate the reinforcement pattern that you've chosen. And so that'll make a little bit more sense when we get into the example. Everybody good? Any questions? All right. So like I said, we're going to do an example start to finish. We've got a 22-foot long beam. It's going to be simply supported, so just hinge and roller support on each end. It's got 1 kip per foot of dead load. Now that dead load is in addition to the beam self-weight. So if the beam weighed, let's say, 400 pounds per foot, that would mean the total dead weight would be 1.4 kips per foot. So I'll have to include that. And then we have the 2 kips per foot live load. Now that's already gone through live load reduction, so we don't really need to worry about that. We're going to use 4 KSI concrete, 60 KSI steel. It's normal weight concrete, so we'll take its unit weight to be 150 pounds per cubic foot. And we'll use a D over B ratio of 1.5 when we get into design mode. And you'll see how I employ that here in a little bit. So with that, let's just get right into it. So here I've got my notebook. Let's see. So the first thing I'm going to do, I'm just going to recap some of the parameters that are important. So write down some of these system parameters. So we have a 22-foot long beam. All right. We have a dead load of 1 kip per foot. Okay, now that 1 kip per foot, again, that's the term that I'm going to use is the term superimpose. So that means the beam has a self-weight, and then we're putting 1 kip per foot on top of that. So if you hear me use the term superimpose, that's what that means. So I'll put a little note on that. Okay, then we have a live load, which is 2 kips per foot. Okay. Now, in terms of material properties, now we have an FC prime of 4 KSI. Now, pop quiz, if we got a 4 KSI concrete, what does that mean for beta 1? 0.85. There we go. So we're going to utilize 0.81 in the example later on, so we might as well go ahead and indicate that. So beta 1 is 0.85. All right. We have FY is 60 KSI. And then while we're at it, I don't know if it's totally necessary since we've been using this value pretty much entirely throughout the semester, but we'll say the unit weight is 150 pounds per cubic foot. Remember, that's a little bit heavier than what regular concrete normally weighs, but again, we bump it up a little bit to account for the reinforcement inside. Okay. Excuse me. All right. So what I'm going to do is I'm going to go through this step by step, just like that design procedure delineates, and when it's all said and done, we're going to have a beam out of this. So step 1 is going to be what? Anybody got their notes on them? We're going to compute the factored moments. So our goal out of this is to get an MU. So that's a moment that's gone through the 1.2 dead, 1.6 live load factoring process. So I scrolled that down a bit. Okay. So we've got the dead load on the beam, and we've got the live load on the beam, but we need the beam self-weight. Now, does anybody remember if you have a beam, let's say it's B wide, H tall, and so long, does anybody remember how you get the self-weight of that beam? You take the unit weight and you multiply it by what? The area. Exactly right. So ultimately what we're going to be employing is W naught. If you ever see me use the term W sub naught, or W sub 0, that's the original weight. So I use that to refer to the beam self-weight. So what we're going to do is we're going to take the unit weight of concrete and we're going to multiply it times B times H. So remember, the total weight of the beam is the unit weight times the volume, and the weight per foot would be that divided by the length. So that's how we get the area. Now, there's a problem, though. I'm in design mode. I don't have a clue what the beam looks like. Okay, I don't know what B or H is because that's the whole point of the problem. Okay, so in order to go through this process, we're going to have to make some assumptions. Now, when you've got more experience in concrete design, you'll be able to look at some of these parameters and go, I bet that beam's going to weigh something like 400 pounds per foot. And that's just something that comes with experience. There's really no simple formula for something like that. But in lieu of that, there are some guides that we can use to make our life a little easier. So let me see. Let me go back to step 1. Okay. So remember we discussed this last time. This is the ACI limits on beams for deflection requirements. And so if you have a beam that's simply supported, you can determine its minimum height or its minimum thickness as L over 16. So now let's keep in mind, these are minimum heights. So if you remember, I said that when it's all said and done, the beam is, the assumption that we make is probably going to be a little lighter than what it actually is. But it's at least close enough for government work to get us started. So here's how I'm going to go about this. All right. So we need some dimensions in order to determine a beam self-weight. So we're going to start off with determining a minimum height. Okay. And the minimum height, I'm going to take that as L over 16. Okay. And I'm taking it as L over 16 because it's simply supported and we're looking at a beam. Is everybody okay with that? All right, okay, and so the length of the beam is 22 feet divided by 16. But if we're looking at beam dimensions, might as well go ahead and convert that just so we can have a general idea of what it is that we're looking at. So I'm going to multiply that by 12 inches per foot so that the answer is in inches, something I think we can conceptualize a little bit easier. And so what does that come out to be? 16.5, and I got seconds on that because I heard that. So 16.5. And then you need a beam width. A rule of thumb, a good rule of thumb, at least for our purposes right now, is to take that beam height and divide it by 2. And you can pretty much always do that at this stage just to get an idea of an initial beam weight. So that's going to be what? 8.25. Do I have a second on that? All right. Yes, sir. You're saying subtract 3 and then use your D over B ratio? You could, and I mean, if you wanted to be a little bit more precise, I guess you could. But keep in mind that we're at an initial phase. Let me say this. When it's all said and done, I'll go ahead and tell you, our beam's not going to look anything like this. But this is just close enough to get a self-weight that we can go with. See, if you wanted, what you could do is you could just assume no self-weight at all, okay? And then when it's all said and done, you get a beam, now you have to include it. If you do that, though, you have a tendency to have to iterate a bit more. So it's just good right now to have a value to go off of. And so at this point, we can be pretty fast and loose with it. Later on, we'll get a little bit more scientific with it. Everybody good? This is good stuff. So far, so good? Okay, so therefore, what we can do is we can get a self-weight. So I'll say, so W sub naught, so what are we going to do? We're going to take 150 pounds per cubic foot. We're going to take 8.25 inches. We're going to take 16.5 inches. Anybody got a problem with that? Units don't work, right? So this and this are in inches. So this is going to be what? Square inches when you multiply this out? So I need to convert square inches into square feet so that it co-aligns with this. So what do I need to do? Do I divide that by 12 or what? 144. So I'll say 1 square feet equals 144 square inches. Now, I'm sure some of you are thinking, well, it would have been feet here. Why did you convert in the first place? Well, I did it for a couple reasons. One, I wanted everybody to have kind of a general idea of what this beam looks like right now. But two, one of the things about reinforced concrete design is that you tend to do a lot of back and forth between kips and pounds and feet and inches. And so I really want you to be pretty comfortable with unit conversion because we're going to do it a lot with this process. So I just want that part to sort of be a non-issue. So anybody got a value for me? 141.8. Do I have a second on that? All right. So that's 141.8 what? Pounds per feet. Okay. And so if we want to convert that to, let's say, kips per feet, that might be 0.14. We'll just say 142. Everybody okay with that? All right. So now we've got a self weight and we've got the dead load and the live load. So what's the next step? If you have an individual dead load and an individual live load in your design mode, what do you need to do? So yeah, 1.2 dead plus 1.6 live, right? Now, is this going to be a dead load or is this going to be a live load? That's a dead load. Why? Because it's not moving. It's not going anywhere. That's a permanent load on the system. So when we factor this, we're going to account for this W sub naught as a dead load. So therefore, the way I'm going to write that is I'm going to say W sub U. So I'll go ahead and factor the loads and then determine a moment. Okay, so that is 1.2, and I'll say that's W sub naught plus W sub D plus 1.6 times W sub live. So in other words, we'll just lump all that together because it's all dead load. Okay? So this is going to be 1.2 times, and so I got 0.142, so we'll say 1.142 kips per foot plus 1.6 times 2 kips per foot. And so that comes out to be what? $4.57. Do I have a second on that? All right. So 4.57 kips per foot. Now, I'm sure some of you are like, oh, good, great, grand, Dr. Mike, who cares? What is that value? Okay. Well, let's bring it back to 312. Let's bring it back to structural analysis. How long is this beam again? 22 feet. Okay. So remember, it's simply supported. So really what that means is this. Let me scroll down a bit. So what that means is I have a beam that's simply supported, all right, and it's 22 feet long. Well, you're exactly right. I'm going to get to that here in a sec. And so I've got W sub U equals 4.57 kips per foot. And so what I'm trying to do is, okay, now I've got a factored load and I have my beam. Now we're in structural analysis land. And so hopefully by now and by what we did last semester, you can take that beam and determine support reactions, draw a shear diagram, draw a moment diagram. That should be old hat by now. So much so that because this beam is so simple and because it's so straightforward, I'm not going to make you draw a shear diagram or a moment diagram every time that we have a beam this simple. I didn't print off copies just because we don't really need all of it, but if you remember, I posted this on Blackboard. These are the shears, moments, and deflections for very, very simple loading scenarios. So this is just all of the structural analysis already done. And if you zoom in to the situation where you have a simply supported beam with a uniformly distributed load, I mean, let's just go back to basics. Like, how would you determine the support reactions, right? You'd take W times L and you'd cut it in half, right? So WL over 2. Well, that's where the support reactions are coming in. So I don't think these formulas are really, mysteries of the universe. This is just what we did last semester, just pre-derived for us. And so because we're in design mode, what we really care about is this. We want the absolute maximum bending moment on the beam for the purposes of design. And so right here, that value is WL squared over 8. Remember we had a homework assignment last semester where I made you all derive that? Y'all remember that? Yeah, so that formula should be somewhat familiar. And so what we can do here is instead of going through the process of drawing the moment diagram and computing the areas under the shear diagram and all of that, we can just keep it simple and say that MU is just WU L squared over 8. So that's 4.57 kips per foot times 22 feet. Remember, you got to square that. Divide by 8. And so that equals what? Excuse me. 276.51. Do I have a second on that? Okay, so let's just keep it simple. We'll say 276.5. Okay. And so we'll underline that because that's kind of an important value. Now remember, this is based on an assumption, okay? We guessed what the beam self-weight looks like. So when it's all said and done, we might need to change that number, especially if the beam ends up being bigger than what we guessed, okay? But I just want you to keep that in the back of your head. Sound good? All right, what's step 2? Step 2 is a lot shorter. MN, there we go. Okay, and so that's the required nominal capacity of the beam. So if MU is what we're putting on the beam, MN is what its required strength is, how much it's got to hold up. And so in order to do that, though, we got to make an assumption. We're going to assume what? There you go. Remember, it's a guess. We would really like it if phi was 0.9, but it might not. We'll see. So MN required is MU over phi. And so that's 276.5 foot kips over 0.9. And so that equals what? 307.2. Do I have a second on that? All right. Now, I'm going to have you do something for me, and you'll see why here in a second, because it's just going to make the value a lot more usable later. Will you go ahead and convert this into inch kips for me? And so how do you do that? What do you do? Do you divide by 12? What do you do? Multiply by 12. There you go. And so MN required equals what in inch kips? 3686.4. Do I have a second on that? Oh. 0.4 and 0.78. You got overruled. I promise, or that's inch kips, sorry. I promise the beam won't fall down as a result of that. And if we were doing this in something like Excel, this would be a non-issue. Because what's going to happen is this, just so everybody's aware, at this stage in the problem, I'm not saying be fast and loose, but a decimal point here and there really isn't going to matter. Because what will happen is this, you'll end up calculating a required width of the beam, and let's say it's 15.8 inches. You're not going to size a beam 15.8, you're just going to round it up to 16. So you're going to round things up a bit, and then when it's all said and done, you're going to analyze the beam as is. So you got a little bit of wiggle room right now. Trust me, it'll be okay now. Everybody good? All right, so what's step 3? So we're going to compute a rho value for the purposes of design, so a reinforcement ratio. Now remember, reinforcement ratios can be small, and that's okay. They're going to be small numbers, okay? And so another thing, remember, you can be real scientific about your rho values, but for the purposes of this problem, we're just going to keep it simple. So we're going to use a rho value of 0.18 FC prime over Fy. Remember, that just comes from an old version of the spec. We don't have to meet that limit anymore, but it's actually a pretty good rule of thumb for design purposes. So we don't have to meet this limit. It's just something to keep in mind. So 0.18 and then 4 KSI over, what was Fy? 60. And so that equals what? 0.012. So do I have a second on that? All right. So that's basically saying that the cross-section should be, what, 1.2% steel? So it's going to come out tiny. That's okay. So far, so good. Any questions? All right. So now the formulas get a little bit hairier. Okay. So what's our next step? We're computing what? BD squared. Okay. So all right. And so this formula gets a little bit messier, but this is where we start to get a little bit more scientific. Based on all of these assumptions, we've got some values where we can now start computing what the beam should look like. So this is going to be Mn over Fy times the following. Okay? And so you have this in your slides. So this is rho design times 1.7 FC prime minus rho design times Fy. Okay, and so definitely on this problem, I want to make sure that we're comfortable with the calc because it's kind of big. And this is 1.7 FC prime. Okay. All right. So to start, Mn required, okay, what was Mn required in inch kips? 3686.4. So this is 3686.4. Again, write those units out. This is in inch kips. Now, Fy. Fy is what? 60 KSI. Now, before I move on, see why I went ahead and had you all convert the moments into inch kips? Because we've got inch kips. We have kips per square inch. So a lot of times in design mode, it makes sense to have your moments in inch kips because you can easily compute your stresses in KSI and all the units work out. All right. Now, what I'm going to do is I'm going to use braces here. This is going to be a real big fraction. On the bottom, we have 0.012, and then 1.7 times 4 KSI minus 0.012 times 60 KSI. So I can cut that off a bit. And then this is 1.7 times 4 KSI. All right. I'm going to hang out here for a second because I want to make sure that you all are getting the same value on this one because this one's kind of big. So first person gets a value, let me know. 5726.3. Am I getting seconds on that? Okay, that is correct. Okay, so if you're not getting 5726.3, I would check your parentheses and how you're doing this. It might be a good idea to compute this denominator separately and then plug that into the rest of the fraction. But yeah, it should be 5726.3. Now let's talk about units. Okay, let's look inside the braces. What's going on with the units inside the braces? We have KSI over KSI. So it cancels. What about over here? We've got kips and the kips. They cancel. But let's just think about it. What are we computing? We're computing a BD squared. What would the units of BD squared be? Say it again. Inches cubed. It's basically a section modulus. So the answer here is inches cubed. So that's basically how big the beam needs to be. Everybody okay with that? Okay. All right. We'll scroll down a bit. Now, unfortunately, that doesn't really tell us anything in terms of dimensions. I'd actually like some dimensions, a B value, a D value. I want to know what's going on with this. So my step 5 is going to be compute required beam dimensions. Okay. So now remind me, in order to determine the proportions of the beam, we were going to assume a D over B ratio. Anybody know what that, remember what that was? 1.5. So in other words, the D is going to be 1.5 of the B. Everybody okay with that? So I'm going to do a little bit of algebra, or a little bit of arithmetic, and you're going to see where I'm going with this. Okay, so if this is D, what's D squared? It's 1.5 squared, which is what? $2.25. Everybody get on that? So 2.25 times B squared, right? Just square each number, right? And so if that's B, or if that's D squared, what would B D squared be? It would be 2.25 times what? B cubed, right? So why is that relevant? Well, we have a limit on BD squared, right? Right? And what was that limit? It was 57, what, 26.3? So I propose then that 2.25 times B cubed has got to equal 5726.3 cubic inches. And so how do I determine what B is? Just solve. So we're going to divide by 2.25, divide by 2.25, and so I get B cubed equals 5726.3 cubic inches over 2.25, and then all I got to do is take a cubic root or raise it to the 1/3 power, whichever your calculators prefer. So and so what does B equal? 13.65. Do I have a second on that? Okay. So this is telling me that based on our assumptions and what we've been looking at, that our beam has to be 13.65 inches. But are we really going to use a beam that is 13.65 inches? No. Okay. So I propose that in order to generate a beam or to fabricate a beam that's reasonable, that makes sense, let's just round that up to the nearest inch. Okay. And so what we will do is we'll use the following. Let's use a 14-inch wide beam, okay? And so that's the width. What about the effective depth? So the effective depth, we're just going to use 1.5 times B, and that's going to be what? 21? Now, that's all we need for capacity, but we do need an actual full height of the beam in order to determine the beam's weight, okay? And so how do we do that? What's our reasonable assumption? Anybody remember? D plus 3, exactly. So the height of the beam, we'll take D plus 3 inches. Okay? So a couple things. One, yes.
So in the case that like say our B was 13.5,
Yes.
we have multiplied like the 1.5 times the 14 still, or times the 13.5?
I'd go with at the end. You know, if you went with 13.5, I'd go with at the end.
You would round it down in that case. It was 13.5, you would have got like 20.25, so you would round it down.
Well, that's a reasonable. This is a reasonable discussion. Let me also say this. Incredibly rarely would I ever round down. I'd probably always round it, because think of what you're talking about. We're talking about the required size of a beam to safely resist these loads. And so if you got it, I'll be honest, even if the number was something like 13.2, I'd always round up to the nearest inch, because I always want more beam to be conservative. Plus, here's another thing. At this stage of the beam, or at this stage of the design process, I'd rather have a beam that's too big, and then at the end, when it's all said and done, it's not very efficient. Then I've got something to chip away at, you know, as opposed to, you know, what if I round down and then at the end of the process the beam is no good? It's almost like now I have to start over again. So I'd rather have a little bit more than I need and chip away at it than the other way around. That's a good question, though. Any other ones? Kinda, but what I would say is this, is I think it gives us a little bit more room to optimize later. Because what we'll do is we'll compute an efficiency, and let's say we computed the efficiency and it was really low. I think it was something like 70%. Well, then we know the beam's too big and we can start chipping away at some things. Whereas if it's 120%, it's way no good. It's like, well, now what? You know? So, this is good stuff. Any other questions? All right. Now, we're not done with the design process because we're missing something. What are we missing? We know how big the beam, we know the size of the beam, but what do we need? We need the steel. Now, for the area of steel required, remember how you compute that. It's really simple. You just take rho BD, okay? But in this instance, hold on, sorry. Because we actually have what the beam looks like, we're going to use the actual physical dimensions of the beam. So in this instance, we're not going to use the 13.65 or whatnot. We're going to use the 14 and the 21. So this is 0.01, was it 1.4? Or was it 1.2? I knew that. I was just making sure you're paying attention. That's my story, and I'm sticking to it. Okay, and so what does that come out to be? 3.528. I'm actually going to write out all the decimals. Right, do I have seconds on that? Okay, all right. Okay. Okay. Let's talk about reinforcement patterns. So we know the size of the beam, but what we don't know is what pattern of steel we're going to go with. I mean, we know we need 3.528 square inches. Okay, we know we need that. But there's a number of different ways we could go about that. Okay, and so I'm going to sort of help you out with this. I'm going to sort of, you know, guide the discussion, if you will, and then you're going to see how this works. Okay, so what I'm going to do is I'm going to draw out a little table. Okay, let me make sure that I put here AS required is 3.528 square inches. I want that sort of up here so that we can kind of see it. All right, so what we're going to do is we're going to have a bar size. We're going to have the number of bars. and we're going to have min width. Okay. Now I'm going to help you out with this at the beginning, and then you're going to sort of drive the train from here on. Okay? What I'm going to do is I'm going to start out, and you'll see why I'm starting out with this here in a second. I'm going to start with number 6s. Okay? Now help me out. How many number 6s do we have to use in order to meet that requirement? 8. Okay? So we have to use 8 of them. Now you picked 8 because the area of steel for that many bars is what? 3.53. Okay. Now, that's what the upper table tells us. What about the lower table? Okay, let's say that I use 8 number 6 bars. If I were to use 8 number 6 bars, how wide would the beam need to be? 17.5 inches. Does everybody see that? So what do you think? Is that a viable option? No, it's not. What is the width of the beam? It's 14 inches. So the width of the beam, so here, let me put this up here. The beam is 14 inches wide. So this would be a great choice because this is like right there, you know. Like it's just enough steel, but we can't use it. We can't use it because we don't have enough room in the beam to put 8 bars in it, okay? So this option, what I'm going to do, I'm going to say this is no good. That option's no good. As much as I'd like to use it, we can't use it because we don't have the room, okay? Everybody see that? Now, let me also say this. I'm doing a lot of writing of this stuff out. When you're doing this practically, you probably don't need to write all this out, and you'll see the pattern here in a second. But I want to write it out and document it so that we can all follow the thought process. So let's go on to the next bar. Let's say number 7s. So you tell me, how many number 7s would we use? 6. Okay, and you picked 6 because the area of steel is what? 3.61. If we were to use 6 number 7s, what would the required beam width need to be? 14.6. Is that a valid option? No. All right. Next one. If I were to use number 8s, how many bars would I use? 5 of them, okay? And so that's 3.93. If you were to use 5 number 8s, what would the required beam width be? 13.3, we'll say 13.3. So what we've got here is number 8, 5. The area of steel is 3.93. And then that is, what'd you say? What was the? 13.3. Now, is that a valid option? That's a valid option. There you go. So this is our first choice that would work. This would be a valid alternative. Okay? Now, let's keep going. Are there any number 9 options? Well, we can't use the 3, so so we'd have to go with the 4. So 4, because the area of steel is 4.00 square inches. And what's the minimum beam width? Somebody else. 12.02, so 12.0. Does that work? Now, if we stopped right now, which option would you go with, the number 8s or the number 9s? Why? Well, it's not the width really isn't really the biggest issue. There's another parameter I want to look at. The area of the steel. This is less steel. Ultimately, it's more bars, but it's less steel. So that means less hit on our wallet. So the smaller area of steel means less pounds of steel per beam. So we always want to go with the lowest number that's just higher. So let's try one more. Let's try the number 10s. How many number 10s would we use? 3. And why'd you pick that? There you go. And what's the required beam width? 10, so 10.3. So that's obviously valid. Now, so between those 3, which would you pick? The 3 number 10s. So let me ask you this. Looking at the number 11s, the number 14s, and the number 18s, is there any iteration that's smaller than this number but bigger than that one? No, right? Because the number 11s go all the way to 4.69. Then you got 4.5 and 4. This is the most economical choice, right? So here, yes? You're exactly right. And so that's something I was going to point out at the end. It's possible if we put this, let's say, in 2 layers, that we could do that. The only thing I would say is I would wait to make that decision until you look at your efficiency at the very end. Because if your efficiency is super low, then you might go with that option and doing that. The only thing is, if you do that, you end up making your beam deeper. And so there's going to be a lot of other issues I want to discuss here at the end, but that is one of them. That's a good point. Everybody good? For in design mode, if you're ever in design mode, I would automatically assume you're in 1 layer, and then, you know, we'll edit accordingly. Sound good? Yes. Well, I wouldn't look at, it's not a matter of being allowed or unallowed. It's this. Your beam is only this wide. Okay? Let's say this is 14 inches. In order to fit 8 bars inside that beam, you need more room than 14 inches, which is why this isn't a valid assumption. Now, in design mode, could you up that to 15 inches? Yeah, you should. You could. I mean, there's no problem with that. But there's something to be said about you want the beam to be as small as possible, but that safely resists the loads. Otherwise, we would just make, you know, beams that are 10 foot deep and, you know, 80 inches wide. You see what I mean? So there's a point when you want your design to be economical. Yes. That's what it's assuming 1.5 inches of cover on each end, the stirrups, the bar diameters, and then a bar diameter or 1 inch between them. So that's what this lower table is computing for you. It's not terribly difficult, but, you know. But yeah. Sound good? So when it's all said and done, we can write out our trial design. Let me scroll down a bit. So our trial design looks like this. Here's our beam. It is 14 inches wide. It is ultimately 24 inches tall, but it has a 21-inch effective depth. And then the reinforcement pattern that we chose was 3 number 10. So this is 3 number 10s. And so the area of steel was 3.82 square inches. What do you think? Okay, so here's what we're going to do next time. Is that beam bigger than our initial assumption? I mean, remember on step 1, how tall did we say the beam was going to be? 16.5. So in initial, assumption mode, we said the beam was only going to be 16.5 inches tall and something like 8.25 inches wide, right? That beam is certainly way bigger than that. And so what that means is that MU, that factored moment, that's too small. It's not. In fact, it's going to be larger. We assume that the beam only weighed something like 142 pounds per foot. It's going to be a lot heavier. Okay, so we're going to have to update that MU. Another thing that we're going to have to do is we're just going to have to straight analyze this beam. compute the capacity, compute the phi value, see if we meet the area of steel requirement, and then ultimately compute an efficiency. And so we're going to do that next time. And then what we're going to do next time, because that isn't going to take too terribly long, is we're going to take this design process and extend it a little bit further and say, well, what if we already knew the cross-section of the beam? What if we were using something like a precast beam or ready-made formwork where we already knew what the beam looked like, and the only thing that we needed to determine was the area of steel? We're going to use the same design aid, but the process is going to be a lot simpler. Okay? And so that'll be what we cover tomorrow, and then I think you'll be pretty much set for your next homework, the homework 4. All right, sound good? That's all I got, everybody. I'll see most of you here in about 10 minutes.